everybody. Hope y'all had a great break. Hope y'all stay safe out there and don't catch the corona. But we back at it, so let's get started. I'm Samuel Howard, the group leader for Group 3, and this is Experiment 3, the refrigeration cycle. So the objective of this experiment is really to analyze the efficiency of a heat pump. To do that, we're going to need some principles that we learned from our thermodynamics classes. First off, let's talk about what the vapor compression cycle is. Shown in the TS and the pH diagrams below, we have the ideal vapor compression cycle. What makes this ideal is the fact that all of the steps are taking place on constant temperatures, constant enthalpies, constant entropies, and constant pressures. So as you can see, we're putting work in and we're ejecting heat from the system, all at constant entropies and enthalpies as well as constant temperatures and pressures. Now, in real life, we know that's not the case. We know as we go between these steps, we can't do that at constant temperatures or constant enthalpies. So as you can see on this graph, as we're going from steps 2 to 3, we don't have a constant temperature like we did in the ideal TS diagram. Same for 5 to 6. And also, as you can see, from 3 to 4, we actually go outside of the vapor dome. Because in reality, we can't stop the process right when it becomes a saturated liquid. So oftentimes we'll go past that point and then go back into the vapor dome as we expand the working fluid. And the reason we can't have constant temperatures or constant pressures or constant entropies is because of inefficiencies in our system. So a lot of times we'll have resistances in our compressors and laminar flow, in turbulent flow, and so we have losses in those resistances. So the major components of the vapor compression cycle are, well, obviously a compressor. We're going to put work into the compressor from steps 1 to 2, and you can see we have ideal graphs here. Again, it just makes it easier to see. So we input work through the compressor, and then from 2 to 3, we expel heat out of the condenser into the high heat bank, which obviously we couldn't do that in nature. Heat doesn't travel to a higher temperature, but by putting work into the system, we can do that. So from 3 to 4, we pass through the expansion valve. And so when the working fluid comes out of the condenser at step 3, it's a liquid. We send it through the expansion valve to become a vapor. As you can see in the vapor dome, from 3 to 4, we go from a saturated liquid to into the vapor dome. And finally, we have from 4 to 1, we have the evaporator. The evaporator is actually going to take heat in from the low temperature environment. As you can see in the TES diagram, we have an increase in entropy, and in the pH diagram, we have an increase in enthalpy, which represents that intaking of heat. An important metric for a heat pump is the coefficient of performance. So the coefficient of performance is the heat taken in from the cold temperature bank divided by the work put into the system, which if we think about it, that makes sense. Anytime we're talking about coefficients of performances or efficiencies, we're looking at what we want out of the system divided by what we put in. In this case, we want to maximize the heat taken from the cold source divided by the work that we have to put into the system. And finally, the real magic of this system is the thermostatic expansion valve. So as you can see, coming in from the right side of the diagram, we have the high pressure medium temperature saturated liquid coming from the compressor. Now it's passing through the thermostatic expansion valve, and as you can see, the working fluid is being throttled through that expansion valve. And what's controlling that throttle is the sensing bulb on the left side of the diagram. What's moving the sensing bulb is the low pressure, low temperature superheated vapor working fluid. And so as the temperature of the vapor increases, it expands, which causes that sensing bulb to move, and then works back around and causes that diaphragm to expand, allowing more working fluid to pass through, which provides greater cooling and lowers the temperature back down and repeats the whole cycle. So that's all. Look forward to, I guess, not seeing y'all in lab, but hearing y'all's feedback. Thank you.